Welcome to ToKCast, episode 23, chapter 11 at the beginning of Infinity, the Multiverse. This is the chapter that personally I've been looking forward to the most, and we're going to approach it a little bit differently. Background for a start is a bit different. This episode's going to contain far less reading from the beginning of Infinity. I don't think this is necessarily crucial for helping us to understand what's happening in chapter 11, but it will just help things along a little bit, perhaps. I don't just want this chapter to blow right by you, as Sam Harris has said of David Deutsch's way of explaining certain powerful but subtle concepts, because once you have understood this chapter, it's one of the deepest explanations of quantum theory that exists out there anywhere, whether in popular science form or even proper scientific text form. So this chapter not only tries to explain the new way of understanding quantum theory, which is basically via the multiverse, but also a new way of understanding the multiverse via David Deutsch. And so we're really looking at the very cutting-edge way of trying to understand reality as explained to us by quantum theory, and the very latest that David Deutsch has published on this. David's given talks, like the one titled, you can look this up online, called Apart from Universes, which attempts to convey some of the other, perhaps more striking and surprising things about the multiverse, apart from the multiple universes bit. As we'll come to see, David's claim that this is actually among the more mundane parts of quantum theory will make sense. When I say mundane parts, the fact that there are multiple universes is really not the most interesting part of the multiverse theory. There's a lot more to it. So to my mind, this chapter really is a level up from the typical explanations of quantum theory, and even a level up from the typical explanations that you hear from other science communicators and physicists when they try and explain the multiverse. And for this reason, it's why I think we need to take a little step back, and that's what I'm going to do here and now in this episode. Also, if you're listening on audio, this one contains a lot of images, videos, and animations to help things along. In particular, I'm going to be trying to explain some experiments, 3 experiments in particular, and without the visuals, one may really struggle in places to understand what I'm describing in certain points. Also, if you're interested, there's essentially a preamble to this episode. In episode 0, if you like, that was episode 22 of ToKCast. It's in audio form only. And the purpose of that is in part to provide some additional material to support these episodes. I think there'll be 3 of them. One charge levelled against the multiverse is that it cannot be tested, so it fails Popper's criterion of falsifiability. But that's incorrect. We'll be discussing that issue throughout these episodes, but if you can't wait, then episode 22, the audio episode, that's available, and I give some details there about the falsifiability of the multiverse, the testability of the multiverse against rival interpretations, and in fact, the testability of the multiverse against classical physics. Now, there's a question that David answers in the next chapter, chapter 12. The chapter 12 is A Physicist's History of Philosophy. And that's about why the quantum multiverse, as first explained by Hugh Everett back in 1955, is still not taken seriously today by a majority of physicists. Although that does seem to be rapidly changing right now. The answer to the riddle, why don't all physicists agree with the multiverse, is basically bad philosophy. But most people watching or listening to this will not be physicists. And so we've got a kind of a 2-pronged problem as I see it. On the one hand, the multiverse remains a minority opinion among physicists. And this might be a cause for concern among some non-physicists. If the supposed expert consensus seems to be against the multiverse among professionals in the field, shouldn't I, as a non-physicist, take that as a bit of a red flag? The answer is no, and the reason why, as I alluded to, will be provided primarily in the next chapter. Okay, I'll have details on that in the next chapter. Suffice it for now to say that the reason is bad philosophy. And I will be covering some of that in these next few episodes about the multiverse. To give a taste of what went wrong, the physicists were quite understandably initially unable to comprehend what was going on with a bunch of problematic observations from various experiments in the early 1900s that led to quantum theory ultimately. What was happening in those experiments, the observations that they were making, were so counterintuitive, and so many ideas were floated to try and explain it, that many working quantum theorists simply gave up even trying to understand it at all and became what are known as instrumentalists. Now, an instrumentalist is someone who regards a theory as useful only insofar as it can predict the outcome of experiments. This has not really happened before ever in the history of science. It would be rather like when Niels Bohr, who came up with some of the early foundational parts of atomic theory, like, for example, his model of the atom called the Bohr atom helps us to explain why the flames of certain elements when they burn, or certain compounds at all when they burn, have a particular colour. So if you're looking at fireworks and you see a green firework, that's usually because of a copper atom there somewhere or other burning. It could be a copper salt, for example, that's burning. Copper salts tend to burn with a green flame. Pure copper itself burns with a green flame. If you were to powder up copper metal and set it on fire, it catches fire very readily, it will burn with a green flame. Now, why green? Well, it's similar to why yellow when you're burning wood. Wood contains carbon and it burns with a yellow flame. Different materials burn with different coloured flames. Of course, most of us are only familiar with wood burning, and so we see that characteristic yellow flame or characteristic red flame in some cases. But every other element has its own characteristic coloured flame. Now, why? Well, on Bohr's model of the atom, the reason why is because the electrons orbit the nucleus at different energy levels. And as the electrons move up and down those energy levels, they can either absorb photons of light or they can emit photons of light. And so if you have a lot of heat, then what's going on is the electrons are being given additional energy, okay, by the flame, by the fire. And when they are knocked up to a higher energy level, because now they've got higher energy due to heat, then they're unstable in that particular position. They want to be at the most stable or ground state, and so they tend to fall back down. So they're originally at a higher atomic level, a higher atomic energy level, and they fall back down to a lower atomic energy level. And in that process, they emit a photon, and that photon is characteristic of the atom in which the electron finds itself. Okay, that all makes sense. So what's that got to do with instrumentalism? Well, at the time when Bohr postulated all this, no one could see atoms at all. There was no chance of seeing atoms at that time. There was no such thing as a scanning tunneling electron microscope, which allows us to see atoms. No one could see atoms. If you're an instrumentalist, what you would have said at that time is, that's an interesting model, Niels Bohr, that you have of the atom. However, I don't believe in the existence of atoms because I cannot see them and no one can see them. So we can use your model in order to predict the colours of flames when elements burn, but we are not forced to believe in the existence of atoms. The best explanation is not that atoms exist. We don't need a best explanation. That's not what science is about. Science is merely about predicting the outcome of experiments. It's merely about allowing us to say what colour the flame will be when you burn a particular atom, not that atoms actually exist. It's about telling us that when you burn a particular substance like copper, you get a green flame. And the reason why, according to atomic theory, is because the electrons are moving up and down. But you're not forced to actually believe in the existence of atoms. It's just a useful mathematical model. Indeed, at the time, there were some physicists. The chief among them was Ernst Mach, who said at the time that he refused to believe in the existence of entities which could not in principle be seen. And that was the status of atoms at that time. But as David Deutsch has explained over and again, science is really about explaining the seen, the colour of certain flames, in terms of the unseen, the movement of electrons around the nucleus of an atom. So we explain the green flame burning in copper that we do see in terms of electrons moving between orbitals around an atomic nucleus, which is a process that we don't see. This is absolutely key to appreciate in science as a general principle. We explain the shining sun that we do see in terms of the smashing together of protons, hydrogen nuclei, in the core of the sun to form helium nuclei that we don't see. We've got no hope of seeing that. It's in the core of the sun at 15 million Kelvin, and nothing can survive 15 million Kelvin if it was attempting to observe what was going on at the core of the sun. We know the Big Bang happened. We explain observations that we have of the cosmos, for example, that there is heat left over at a temperature of 2.7 Kelvin above absolute zero that permeates all of space. We see that, we observe that, and we observe the so-called Hubble shift of galaxies. All the galaxies, not all the galaxies, many of the galaxies out there are redshifted away from us and appear to be moving away from us. And finally, we see that around about 75% of all the atoms in the universe are hydrogen, and about 24% or something like that are helium. And this ratio is only explained by the Big Bang. So we see these things, the ratio of the elements, we see the movement of galaxies, we see heat left over in the universe, but we do not see the Big Bang. We cannot see the Big Bang. We can't travel back in time to 13.7 billion years ago and see the Big Bang. So we're explaining what we do see, those three things I mentioned, the three pieces of evidence, in terms of the unseen. the actual occurrence of the Big Bang. And of course, David's favourite example here is dinosaurs, and he's talked about this in many different places. What we see are fossils, rocks, certain patterns in rocks. Yeah, they look like dinosaurs, but only in retrospect, only once you know that dinosaurs exist. You never see a dinosaur. No one's ever seen a dinosaur. Likely, no one ever will see a dinosaur. What we see are rocks. This is a rock. This is a series of rocks that people have dug out of the ground and assembled together, and my gosh, it looks like a T-Rex. But it's not a T-Rex. It's not one of these. Rocks are ossified bones. They aren't even dinosaur bones, they're rocks, because over time the dinosaur bone material itself has been replaced by rocks. It's a form of metamorphic rock. We don't see actual dinosaurs. We explain the scene, what we can see, the fossils, in terms of things we cannot see, the dinosaurs. So one, the unseen stuff, is an explanation of the other, the seen stuff. It's an interpretation. And the denial of the reality of dinosaurs by, say, some hardcore creationists, they might say it's a test of our faith. Some creationists have asserted this, is irrational. It's irrational because it's far too easy to vary. You can go all the way back to episode 1 of this ToKCast series, all the way back to chapter 1 of the beginning of infinity for more on that. So that's the philosophical context within which we need to couch this whole discussion of the multiverse. The explanation of our observations of certain experiments in the field of quantum physics. I'm going to discuss 3 experiments before getting to the beginning of infinity at all, just to set the stage. Now, the first one is known as Millikan's experiment, and it demonstrates the photoelectric effect. And the photoelectric effect is about how light can actually move particles around. And this is evidence that light is not a wave. It decides between 2 models of light. On the one hand, the idea that light is a wave, and it cannot possibly knock particles out of the way. It can only vibrate particles up and down. It can't knock them away. And the particle theory of light, on the other hand, where the particles of light are kind of like little billiard balls, and they can knock things out of the way. They can physically collide. And that's a good way of thinking about things, that particles can actually physically collide and bounce off one another, whereas waves can go through one another. And if you've been to the beach, you've actually seen water waves do that. Now, the second experiment is known as the Zehnder Interferometer. And in this experiment, we can't possibly explain the outcome, if you set up the experiment just right, and I'm going to spend some time explaining that. You can't explain the outcome without understanding that there must be 2 photons in the apparatus, even though you only ever fire 1, which is astonishing. You fire 1 photon at the apparatus, and the only way to understand the result of the experiment is by recourse to postulating the existence of a second, equally real photon. Now, in fact, what's going on is a little bit more complicated than that. The 1 photon differentiates itself into 2 groups of fungible photons. We're going to have to unpack a lot of quantum theory in order to understand what I just said there, but we'll get to that. The third experiment is Young's twin slit experiment, and this is the experiment that was discussed in David's first book, chapter 2, Shadows. And so I'm going to be doing a little bit of reading from chapter 2 of The Fabric of Reality. Okay, before I get to those 3 experiments, I'll just have a little personal reflection here, indulge me for a moment, because though there are many reasons today that people are becoming more and more attracted to the work of David Deutsch, back in 1997, my own reason, and I think I speak for many others, was that I was struggling at university to understand the basics of quantum mechanics. What I was presented with in lectures as a physics undergraduate was the mathematical formalism. We solved kind of puzzles or did exercises in quantum mechanics, rather like doing, high school mathematics. But unlike school maths, which was just about abstract numbers lots of the time, in quantum mechanics at university, the numbers are supposed to represent parts of the physical world, or the symbols are supposed to represent parts of the physical world, how particles and other things actually behaved. But it was near impossible to understand as it was presented to me. What I was offered was instrumentalism of the sort that I just mentioned before. You have these formulae, and you have a process whereby you predict the outcome of the experiment, but you're not really supposed to ask what's going on during the experiment. The maths allows you to simply predict the outcome of the experiment. And so it's a tool. That's why it's called instrumentalism. It's an instrument for predicting what happens in the experiment. But you don't ask what actually is going on in the experiment. Now, if we didn't get instrumentalism, maybe 5% of the other time, the lecturer or the tutor would mention something like wave-particle duality. And in fact, this is even what high school teachers today will do. They'll talk about wave-particle duality, that a photon or an electron is sometimes a particle and sometimes a wave, or simultaneously both a particle and a wave at the same time. Now, given that a particle is something that's isolated at one point in space, and a wave is something that's spread out through space, you can't simultaneously be isolated at a point and spread out at the same time. This violates the law of the excluded middle. It violates logic. But in fact, some people who teach quantum mechanics will say, well, classical logic doesn't apply. And of course, if you're going to give up on classical logic, you're really giving up on reason altogether. Okay, you're entering into woo-woo land. We must obey the laws of logic. Otherwise, we're speaking nonsense. But whatever the case, we were reassured that if we were completely confused, that it was no cause for concern, really, because very famous physicists would say things like, if you think you understand quantum mechanics, you don't understand quantum mechanics. And this was supposed to be reassuring. But I was doing a physics degree back then, and I wanted to understand this stuff. Irrationality didn't sit well with me. It was one of the reasons I sort of migrated into philosophy eventually. I was thinking, how can something be isolated at a point, not spread out in space, and spread out in space all at the same time? I hated all that kind of talk. Now, I read some of Paul Davies' books on quantum mechanics. He wrote The Mind of God. He wrote various other books that had a strong science component to them, and in particular, quantum theory. He was often a bit of a Mysterian. He really revelled in the mystery of quantum mechanics, which was interesting, but I wanted to solve the mystery. I needed to understand quantum theory. But to Paul Davies' credit, in many of his books, he actually relayed theories of many different physicists, and in particular, this is a fantastic one, the ghost in the atom. And it's got interviews with lots of different physicists. And one of the physicists that is interviewed in the book is David Deutsch. And in the interview, he explains the multiverse and he explains how it's testable. David was the first one to come up with an experimental test for the multiverse against rivals, okay? And we're going to talk about that test. I remember at the time when I did read that book with the interview with David, I was confused at first. But I'm going to explore what he does say as we move through this series, in particular about how the multiverse is a testable theory. Now, it was sometime in around 1997 when I picked up this book. Although, not exactly this one. My original Fabric of Reality, a little paperback, I lent to a friend, and it never came back. So I've got many other copies now. That's the nice hardcover book version. And this book I've mentioned before has an excellent recommendation from Paul Davies on the back. And so, seeing Paul Davies recommend this book, of course, I picked it up straight away. And in that book, in Chapter 2, Shadows, David explains the multiverse perfectly clearly. And it was then that I was completely convinced. I finally felt that I understood who was right about how to understand quantum theory. It was the people on the side of the multiverse. It was the only one that made sense. We didn't have to give up logic. We didn't have to give up common sense. We didn't have to give up any other part of science or rationality. We just had to accept the fact that the universe, that reality rather, was much, much bigger than what anyone had thought before. And this wasn't particularly, it was cool. It was kind of really interesting, but it wasn't so shocking that I was going to say, no, that's ridiculous. I can't possibly accept that. It made sense. It was no more shocking to me than, I guess, as a child, learning that there are other planets out there beyond the Earth. Or later on, learning that there are other planets going around other stars. Or that there are other galaxies. Well, now we know there are other universes. This was cool, but it wasn't a great shock to me. But some people are still shocked. It's certainly amazing, but lots of stuff is amazing. It's amazing that we're made of atoms. It's amazing that galaxies exist beyond our own, that the universe is as big as it is, that cells, tiny as they are so remarkably complicated, that all of life on Earth apparently has been extinguished almost completely around about 5 times in the history of the planet. It's amazing that the centre of the Earth is solid iron, but the outer core of the Earth is liquid iron, and that generates a magnetic field that protects us from the sun. So I guess, amazement is not a reason to reject something. It's a reason to be really interested in it. And I don't find it any more amazing that there are these parallel or almost parallel universes out there than any of those other things that I've just mentioned. They're just amazing parts of science. But one reason to reject a scientific theory is when it violates logic. And the other interpretations of quantum theory do exactly that. They violate logic or common sense. And we'll talk about that. So we don't reject things because they're amazing. Not in science or anywhere else. But we can reject things if they violate common sense. And especially if they violate logic. And a lot of these alternatives do violate logic.
You have no respect for logic. And I have no respect for those with no respect for logic. You're a very stupid person.
Okay, so that's kind of right. If you're trying very hard to understand a thing and the explanation you're getting isn't working, it's not necessarily all your fault, or at least not exclusively your fault. It can be very much the fault of the explainer. And that might be quite right. You could be proficient at one part of a particular subject and completely ignorant about another. I think it is a bit of a travesty that quantum theorists, professional physicists, don't all endorse the multiverse. And again, we'll come to that in the next chapter. I did meet Paul Davies once, back in about the year 2003 in Sydney. We were coincidentally at a pub together for an event called Science in the Pub, and the debate raging on stage was between a group of astronomers about the definition of a planet, a matter that would be resolved about 3 years later in 2006. But I wasn't really interested in that matter as soon as I saw Paul Davies. I immediately asked about, as soon as I went up to him and introduced myself, I asked him about David Deutsch and the multiverse. And sadly, pleasant as the conversation was, and interesting as it was, and excited as I was to speak with him, and I got his autograph, and we discussed lots of other things, the response about the multiverse was essentially, I don't have time to explain why it's not correct. But later I was able to read some more of Paul's thinking and watch some more interviews with him, and he thought it, and this is probably one of the most common criticisms of the multiverse, that it violates Occam's razor. So there's too many things to explain the one thing that we do observe. But this understanding of Occam's razor is, in my opinion, completely fallacious. Occam's razor is not about increasing the number of entities. It's about increasing the number of assumptions. It would be like saying we shouldn't postulate the existence of other planets out there that we cannot see just because we can see some here in our solar system and out to a few hundred light years away from the Earth. There is no reason to think that the entire galaxy is filled with planets, let alone galaxies in the rest of the universe. That would violate Occam's razor. We're proliferating the number of planets beyond all reason. Well, of course we're not. It's quite reasonable to presume there are other planets out there in the universe, given what we've already observed here in our solar system and indeed in our local neighbourhood here in the galaxy. So I think it's completely wrong when people talk about Occam's razor in this way. Now, even when some physicists are right about the multiverse, they can still kind of be wrong. I don't generally mention names, but I've been called out by some people watching these videos that I don't mention names enough. So I'll mention one more name. Another person I respect greatly, Sean Carroll, quantum physicist. He's a supporter of the many worlds interpretation as well. He supports the multiverse. He gave a quite good defense of it recently on the Infinite Monkey Cage. They had an episode, if you haven't listened to that podcast, it's quite entertaining. Robin Ince and Professor Brian Cox have that, and they did one on, coincidentally, the most recent one. So I'm recording this now in February of 2020. So if you're looking for it some years hence, The Infinite Monkey Cage in about February 2020, was all about quantum mechanics and in particular the multiverse. Both Brian Cox and Sean Carroll support the many worlds interpretation. But I've heard Sean in other situations give interviews about the multiverse. I think he was on, well, both Joe Rogan and Sam Harris. And during those interviews, he insinuated that the only problem with the multiverse is it's not testable. So this is kind of disappointing. He doesn't understand. There's two tests, at least, that I'm aware of the multiverse theory, and we're going to get to those, that I regard as tests of the multiverse theory. One that was discussed in my previous episode about the fact that if you run an interference experiment multiple times, certain kinds of interference experiment, in particular the double slit interference experiment for single particles, you don't get the same outcome each time. You don't get the same outcome each time because you're finding yourself in a different universe literally each time. Science should produce the same results every single time you run the experiment, but this is a case where you don't get the same results every single time, and that would indicate that you're approximating all the different possibilities, all the different universes that could possibly exist. This is a test, okay? And I'll get to that again later. And so the problem with Sean's claim that the multiverse isn't testable is he then thinks simultaneously that because it's not testable, he thinks that this is a reason that falsification is overrated, or a reason even that physics has moved beyond falsification. And I heard Sabine Hoffenstatter say the same thing online recently as well. A lot of physicists have said this. I should qualify that. A lot of theoretical physicists have been saying this. That the Popperian criterion of demarcation, of falsification, is old hat. We don't need it anymore. We've moved beyond it now. So in the case of Sean, he endorses the multiverse, but for the wrong reasons in part. And Brian Cox, he does endorse the multiverse in some moods, but with hesitation, it seems to me, and hedges, and with sort of dodges in one of his recent books. I don't know that he even uses the term multiverse. Okay, he just claims that about simultaneous realities occurring at the same time. It's the same thing. It's the same concept. It's like multiple histories as well. It's basically multiple universes, just with different language being used. Okay, so that's enough here. I'm just, I guess, emphasizing how difficult it is to find good sources on the multiverse. My own sources here moving forward right now come down to 4 of them. Okay, there's 4 sources I'm going to be using for these. Firstly, my own recollections and recent survey of the fundamentals in textbooks and stuff. Secondly, Paul Davies' book. Okay, so I'm actually going to be going to this and what David says in this book here in his interview with Paul Davies. David Wallace is my third source. Okay, excellent Professor David Wallace, professor of or philosopher of physics, and of course David Deutsch in The Beginning of Infinity, but not only Beginning of Infinity this time around, but The Fabric of Reality. And substantially his paper, The Structure of the Multiverse as well. Okay, so let's move into the first of our experiments. And the first experiment is the experiment that demonstrates that light is in fact a particle. Okay, so this is a cartoon of the photoelectric effect. And we can see here where, and it's from Physics Education Technology at the University of Colorado. So you can type in PHET and you can find this online and play with it. You can see here we can play with the intensity of the light, putting out some red light there. And over here, what we've got is some metal, okay, on the left-hand side there. And the metal is having red light shone on it. Nothing's happening. Red light has a very long wavelength. It's got low energy. The photons have low energy. And so even if you turn up the intensity, which means you're shining more and more photons of light, you're throwing more and more photons there, nothing's happening. Nothing's happening because none of the photons have enough energy to knock the electrons out of the way. Now, if I reduce the wavelength, I increase the frequency, increase the energy, there's a point at which, look, electrons come out of that surface. This is called the photoelectric effect. Of course, you can do this in real life and actually do. I've done this in real life. There's a video online of me doing this in real life. It shows how there's this thing called the threshold frequency. So below the threshold frequency, no light gets emitted, okay, around about there. But if you increase the frequency, then you do get emission of electrons. The intensity never makes any difference if you're below that threshold frequency. Okay, so that's the photoelectric effect. And so what's going on there is if light was a wave, if it was truly a wave, now I guess a way to think about this is if you're a swimmer or a surfboard rider and you're out beyond the breakers on the ocean, and then you're bobbing up and down as the waves pass, you don't tend to be carried one way or the other by the wave. You just move up and down. You vibrate in place. You don't get carried horizontally by the wave. You can't be knocked out of position by the wave, unless it's breaking, and then in that case it ceases to be a wave in the normal way we think about them. Waves also tend to pass through one another as well. They can pass through matter, just as sound can vibrate through a window. It doesn't cause the window to move. Now, on the other hand, particles can collide one with another, and they can knock each other out of the way. So if light is a wave, then as it strikes the surface of the metal here, and it could be cesium, it could be sodium, we use active metals because they tend to release electrons more easily. Then if you've got low energy light, something like red light, then what should happen is if you wait long enough, then electrons should come out because they will slowly absorb the wave energy. And then electrons will come off the surface. But that's not what happens. What you need to do is to exceed a certain frequency, exceed a certain energy of the photons. Because on the particle theory of light, what's going on is a physical collision. And once you have enough energy, enough kinetic energy, you can physically knock the electron out of the atom. And that's really what's going on here. A physical collision between a particle of light and a particle of electricity, namely the electron. And you can detect these electrons. Now you can go to my YouTube channel. I think this is one of the first videos I ever made. And this is an hour-long video. Not really recommending anyone watch it unless you're really keen. All about the photoelectric effect experiment. And so I take a bit of kit, the actual apparatus, and go through it. Go through shining light onto a bit of cesium metal that's hidden inside of a black box. So it's difficult to see the full details, but I do go through it in excruciating detail, all the way down to calculating what Planck's constant is by plotting a whole bunch of data here. So it's interesting if you're a high school physics student or physics undergraduate perhaps, but otherwise just know that it's there if you really are curious about the photoelectric effect. It's there. There's an hour's worth of me talking about the photoelectric effect. Okay, so that's the photoelectric effect. That shows that light genuinely is a particle. Now this is the Zehnder Interferometer, and it's available at this website. You can play with it yourself. So we're going to try and understand this. I'm going to take a few moments to understand this. What's going on? Over here, I can fire photons from a laser or something, one at a time. And they're going to hit something right here that I'm indicating called a beam splitter. Another word for a beam splitter is a half-silvered mirror. And a half-silvered mirror is like, when you watch TV shows and the detectives are interviewing the criminal and the criminal's in the room locked up with an interrogator, a single interrogator, and then behind the glass, behind one-way or two-way glass rather, are all the other detectives watching what's being said. Well, that mirror, that's a half-silvered mirror. You can see through in one direction, but not in the other direction, so long as the room where the interrogation is taking place is lit very brightly, and the people in that room can't see the others that are on the other side of the mirror. Okay, so that's what this thing here is, the beam splitter. The beam splitter is a half-silvered mirror. And you can make a beam splitter to send through 10% of the light, or 20% of the light, or 50% of the light. And this is what's used in this experiment, is a beam splitter where for every photon that you send through, it's got a 50-50 chance of either going through or being reflected. Okay? On the front of the beam splitter is silver. Okay, it's got metal there, highly shiny, reflecting material, and so photons can bounce off it. But also on the back, there's glass. Okay, some photons have enough energy to go through, some by chance, and some will bounce off. Okay, right. So firing a photon will result in 50% going through the half-silvered mirror and 50% bouncing off the half-silvered mirror. And then from there, we've got two other mirrors. We've got mirror 1 and mirror 2, and these are normal mirrors, okay? These aren't half-silvered or anything like this. So 100% of photons that hit here will go this way to detector 2, and the other half will go to mirror 1 and through to detector 1, okay? So if we fire a photon, well, we don't know which way it's going to go. Is it going to go through here or go through here? So let me just fire one and see what happens. Fire. Don't worry about the fact that it's appearing to split in two. Just notice that it set off detector 2. And so in that case, it appears, the common sense thing would be, it's gone bang, bang, and over here. The photon apparently hasn't gone that way, apparently. Okay, let's do it again and see what happens. And it's been detected at detector 1 this time. And we've got 1, 1. So we've got a 50-50. Okay. Well, let's just continuously fire and see if we maintain that 50-50. Because 50-50 would make sense, right? If there's 50% going through the beam splitter and 50% bouncing off the beam splitter, then we should expect these numbers to roughly approximate 50-50. We're a bit out of 50-50 at the moment. But if we continue to let it run, or we fast forward, let me fast forward. Let's stop the continuous. And let's do 100 all in one go and see what happens. Okay, we've got 5 and 4 out of 9. So that's close to 50-50. If we got exactly 50-50, that would be a bit strange. 55, 54 out of 109. So that's a pretty good 50% rate in detector 1 and 50% in detector 2. So far makes perfect sense. All right. Clear. Now I'm going to take a second half-silvered mirror, okay, a second beam splitter, and put it there. Now what do we expect happens? Well, you might expect, okay, well, 50% go this way, bounce, 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 okay, or through, and 50% go this way, bounce, bounce, and could either go that way or that way. So a quarter of the photons coming this way will end up at detector 1, a quarter will end up at detector 2, and if the photon's being transmitted through this first beam splitter, a quarter will end up at detector 1 and detector 2. So we should still end up with 50-50. It still looks symmetrical, doesn't it? Let's see what happens. Let's fire one and see what happens. Okay, detector 2. Fire another one. Detector 2 again. Continuous fire. Well, would you look at that? It seems like detector 1's not being set off ever. What the heck is going on? And if I stop the continuous and we just do 100 all in one go, yes, 100% go to detector 2. They're always and only ever going to detector 2. Why? This animation gives some clue. It's showing that the mirror is causing the photon that is coming out of the laser or wherever to literally split into two photons. Now, technically speaking, we'll bell the cat right now. What's going on is that the photon is not a single photon in a single universe. It's a multiversal object. It's a photon that exists in many, uncountably infinite probably, universes. And when it encounters the half-silvered mirror, it splits into two fungible groups, two groups that are differentiated only by the fact that one of them heads towards mirror 1 and the other group heads towards mirror 2. They both combine then at beam splitter number 2, and that results in them all going to detector 2. Now, but why? Why should it be detector 2 and not detector 1? Couldn't it just be simply be detector 1? And why isn't it 50%? So just a point of clarification or emphasis. The photoelectric effect tells us that there's no such thing as half a photon. You don't get half photons. So if you were to place a detector before mirror 1 or before mirror 2 and perform the experiment, you would find that only one of the detectors ever went off. Only one of the detectors would ever go off. You would only ever detect one photon. This demonstrates that the photon does not split in half in our universe. So when I move forward in this explanation and talk about the splitting of the photon, what I mean is the splitting of the multiversal object, which is called the photon. We exist in a multiverse, and so therefore, when the photon encounters the half-silvered mirror, in half of the universes, it heads towards mirror 1, and in half of the universes it heads towards mirror 2. Now you and your detector are only in one universe, so you cannot possibly detect both simultaneously, both the paths simultaneously. But the way that we reason towards the existence of both paths is the fact that the photon only ever ends up in detector 2. So the multiversal object, that is the photon, does in fact take both paths. You can only ever detect one path, but it is the existence of both paths that explains why the interference happens such that the photon only ever goes and lights up detector 2. Okay, so this is caused by something known as the phase of the electrons. So phase has something to do with wavelength, but when we're thinking about photons, we really just need to think of phase as a quality of the photon. There's such a thing as superposition. So here's a little animation here I just Googled, and you can imagine these as two kind of water waves that encounter one another. When the crest here coincides with the crest there, the addition of the two causes a big crest there. When you've got a crest and a trough, then they cancel each other out. This thick blue line is showing what's called the resultant, the net effect of the two waves above adding together. So there's a point where you get 0. The two waves can add together to give 0. And so that's precisely what's happening over here. The two photons that could travel towards detector 1, cancel each other out. They destructively interfere. But the photons that are heading towards detector 2 constructively interfere. Why should that be? Well, if you know a little bit of physics, reflections from mirrors cause a phase change. So if the photon that bounces off here was originally kind of an up, we think of it as an up bit rather than as a down bit. Okay, so we've got troughs and crests. If the phase of that photon is up as it comes out, then it will be down as it's reflected off. It changes from being up to being down. And then as it reflects off this mirror again, reflection causes a phase change. It goes back to being up. And so it's up as it goes through here. Now, the one that's transmitted here in the other universe, as it goes through the beam splitter here, there's no phase change because of no reflection. There is a phase change over here. So if it was up coming out here, then it's down here. The key to understanding this, and this is a very subtle point to get into the technical details, is that the second beam splitter here, the reflection that can happen there is different to the reflection that can happen here. Here, the metallic side that reflects is encountered before the glass. So it's on the outside of the glass. So the reflection happens and you get this phase shift at this point. However, when a photon passes through glass first and then hits the rear of the beam splitter, causing reflection up to detector 1, the phase change is different. It in fact doesn't happen. The phase change doesn't happen there. Now, there are other complications with this. Namely that as light, in the form of photons, passes through glass, it is refracted. Refracted means bent. And when it's bent, the optical path length, the distance that it travels, is technically further than what it is through air. The net consequence of all these factors, the refraction through the glass, the fact that one of the photons encounters the silvered side first, and the other photon encounters the glass first, has the overall effect of causing destructive interference to detector 1 and constructive interference to detector 2. And so we end up with all of the photons going to detector 2. What on earth has this got to do with the multiverse? Remember, we only fired one photon here. In order to explain why that one photon always ends up at detector 2, we have to invoke the existence of a second photon traveling up to mirror 1 that combines with the photon in such a way that it always ends up detected at detector 2 and never at detector 1. We have to postulate the existence of two photons to explain what one photon is doing. The one photon splits into two groups and then recombines into one. It's more profound than that. The one photon splits the universe into two and then recombines the universes into one. That's what interference is. Interference is the rare example of where differentiation between universes in the multiverses happen and then they're recombined together again. Now, if you're not convinced by that, don't worry. We've got a third experiment to talk about, and I think this really is the clincher. It was certainly the clincher for me. Oh, before I leave here, let's just talk about this excellent paper here. Okay, hopefully you can just see that on the screen. How does a Zehnder Interferometer work? By Zetti, Adams, and Tocknell in teaching physics. So from the physics department at Westminster School. It's excellent. It goes through a complete explanation, not in terms of the multiverse, but if you're interested in the algebra here and the mathematics of what is going on, it's a very simple algebraic argument about the physical makeup of those beam splitters and how the phase of the light changes, the phase of the photon changes. It's very short. It's only 3 pages with some diagrams there. But if you're interested in the details of this, if you're an undergrad or if you're at school trying to understand this or you want to understand this, great little introduction there. But not in terms of the multiverse. No one ever uses the multiverse. Okay, so now I'm going to do some readings from the Fabric of Reality to try and really push this home, this idea that the universe is larger than we think. Okay, so this is from the Fabric of Reality, Chapter 2, page 39, and David writes, Figure 2.6, should be up on the screen now, shows, at roughly its actual size, a part of the pattern of shadows cast 3 meters from a pair of straight parallel slits in an otherwise opaque barrier. Now, what might that look like? So that's what this looks like. So the experimental setup is like this. We have a source of photons. We can fire them one at a time. Then there's a barrier. And the barrier's just got 2 very narrow slits there. And behind on the screen, we end up, if we fire enough of them over time, we end up with this thing called an interference pattern. Okay, and David's picture is a lot clearer about what's going on there. The slits are 1/5 of a millimeter apart and illuminated by a parallel-sided beam of pure red light from a laser on the other side of the barrier. Why laser light and not torchlight? Only because the precise shape of a shadow also depends on the colour of the light in which it is cast. White light, as produced by a torch, contains a mixture of all visible colours, so it can cast shadows with multicoloured fringes. Therefore, in experiments about the precise shapes of shadows, we are better off using light of a single colour. We could put a coloured filter, such as a pane of coloured glass, in the front of the torch, so that only light of that colour would get through. That would help, but filters are not all that discriminating. A better method is to use laser light. For lasers can be tuned very accurately to emit light of whatever colour we choose, with almost no other colour present. So there we can see the shadow cast by a barrier containing 2 straight parallel slits. So this is what you get. If light travelled in perfectly straight lines, the pattern in figure 2.6 would consist simply of a pair of bright bands. Okay, so you end up with just 2 of them. 1/5 of a millimeter apart, too close to distinguish on this scale, with sharp edges and with the rest of the screen in shadow. But in reality, the light bends in such a way as to make many bright bands and dark bands, and no sharp edges at all. If the slits are moved sideways, so long as they remain within the laser beam, the pattern also moves by the same amount. In this respect, it behaves exactly like an ordinary large-scale shadow. Now, what sort of shadow is cast if we cut a second identical pair of slits in the barrier, interleave with the existing pair, so we have 4 slits, 1/10 of a millimeter apart? We might expect the pattern to look almost exactly like 2.6. After all, the first pair of slits by itself casts a shadow in figure 2.6. And as I have just said, the second pair by itself would cast the same pattern, shifted about 1/10 of a millimeter to the side, in almost the same place. We even know that light beams normally pass through each other unaffected, so the two pairs of slits together should give us essentially the same pattern, though twice as bright and slightly more blurred. Now, a 4-slit apparatus looking would be something like that. So here we've got 4 slits. And then we see bright bits and dark bits. Okay, they're the shadows and these are the bright bits. Okay, if you're actually doing the experiment, this is what you see. So you increase the number of slits and you see this sort of thing. So just to hammer this point home, if you've got one slit, you get this big long diffraction pattern. Okay, lots and lots of light with one slit. If you increase the number of slits, in other words, increase the number of places through which light can come, you seem to increase the number of shadows, right? That's rather weird. Yeah, and more shadows here. Less light. More slits, less light compared to one slit. That's phenomenal, isn't it? Okay, well, David's going to explain that. So let's keep going. Back to fabric of reality. The real shadow of a barrier with 4 straight parallel slits is shown in figure 2.7a. Okay, so over here in 2.7a, we've got a picture of these two things. Picture A, that's the 4-slit one, and B is 2 slits. So David writes in Fabric of Reality, the 4-slit shadow is not a combination of 2 slightly displaced 2-slit shadows, but has a new and more complicated pattern. In this pattern, there are places, such as the point marked X, which are dark on the 4-slit pattern, but bright on the 2-slit pattern. These places were bright where there were 2 slits in the barrier, but went dark when we cut a second pair of slits for the light to pass through. Opening those slits has interfered with the light that was previously arriving at X. So adding 2 more light sources darkens the point at X. Removing them illuminates it again. How? One might imagine 2 photons heading towards X and bouncing off each other like billiard balls. Either photon alone would have hit X, but the 2 together interfere with each other so that they both end up elsewhere. I shall show in a moment that this explanation cannot be true. Nevertheless, the basic idea of it is inescapable. Something must be coming through that second pair of slits to prevent the light from the first pair from reaching X. But what? We can find out with the help of some further experiments. First, the 4-slit pattern of figure 2.7a appears only if all 4 slits are illuminated by the laser beam. If only 2 of them are illuminated, a 2-slit pattern appears. If 3 are illuminated, a 3-slit pattern appears, which looks different again. So whatever causes the interference is in the beam. The 2-slit pattern also reappears if 2 of the slits are filled by anything opaque, but not if they are filled by anything transparent. In other words, the interfering entity is obstructed by anything that obstructs light, even something as insubstantial as fog. But it can penetrate anything that allows light to pass, even something as impenetrable to matter as diamond. If complicated systems of mirrors and lenses are placed anywhere in the apparatus, so long as light can travel from each slit to a particular point on the screen, what will be observed at that point will be part of a 4-slit pattern. If light from only 2 slits can reach a particular point, part of a 2-slit pattern will be observed there, and so on. So whatever causes interference behaves like light. It is found everywhere in the light beam and nowhere outside it. It is reflected, transmitted, or blocked by whatever reflects, transmits, or blocks light. You may be wondering why I'm labouring this point. Surely it is obvious that it is light, that what interferes with photons from each slit is photons from the other slits. But you may be inclined to doubt the obvious after the next experiment, the denouement of the series. What should we expect to happen when these experiments are performed with only 1 photon at a time? For instance, suppose that our torches move so far away that only 1 photon per day is falling on the screen. What would be seen? If it is true that what interferes with each photon is other photons, then shouldn't the interference be lessened when the photons are very sparse? Should it not cease altogether when there is only 1 photon passing through the apparatus at any one time? We might still expect penumbras, since a photon might be capable of changing course when passing through a slit, perhaps by striking a glancing blow at the edge. But what we surely could not observe is any place on the screen, such as X, that receives photons when 2 slits are open, but which goes dark when 2 more are opened. Yet that's exactly what we do observe. However sparse the photons are, the shadow pattern remains the same. Even when the experiment is done with 1 photon at a time, none of them is ever observed to arrive at X when all 4 slits are open. Yet we need only close 2 slits for the flickering at X to resume. Could it be that the photon splits into fragments, which, after passing through the slits, change course and recombine? We can rule that possibility out too. If again we fire 1 photon through the apparatus but use 4 detectors, 1 at each slit, then at most 1 of them ever registers anything. Since in such an experiment we never observe 2 of the detectors ever going off at once, we can tell that the entities that they detect are not splitting up. So if the photons do not split into fragments and are not being deflected by other photons, what does deflect them? When a single photon at a time is passing through the apparatus, what can be coming through the other slits to interfere with it? Let us take stock. We have found that when one photon passes through this apparatus, it passes through one of the slits. And then something interferes with it, deflecting it in a way that depends on what other slits are open. The interfering entities have passed through some of the other slits. The interfering entities behave exactly like photons, except they cannot be seen. I shall now start calling the interfering entities photons. That is what they are, though for the moment it does appear that photons come in two sorts, which I shall temporarily call tangible photons and shadow photons. Tangible photons are the ones we can see or detect with instruments, whereas the shadow photons are intangible, they're invisible, detectable only through their interference effects on the tangible photons. Later we shall see that there is no intrinsic difference between the tangible and shadow photons. Each photon is tangible in one universe and intangible in all the other parallel universes, but I anticipate. What we've inferred so far is only that each tangible photon has an accompanying retinue of shadow photons, and that when a photon passes through one of our 4 slits, some shadow photons pass through the other 3 slits. Since different interference patterns appear when we cut slits at other places in the screen, provided that they are within the beam, shadow photons must be arriving all over the illuminated part of the screen whenever a tangible photon arrives. Therefore, there are many more shadow photons than tangible ones. How many? Experiments cannot put an upper bound on the number, but they do set a rough lower bound. In a laboratory, the largest area that we could conveniently illuminate with a laser light might be about a square metre, and the smallest manageable size of the holes might be about 1,000th of a millimetre. So there are about 10 to the power of 12, a trillion, possible hole locations on the screen. Therefore, there must be at least a trillion shadow photons accompanying each tangible one. Thus we have inferred the existence of a seething, prodigiously complicated, hidden world of shadow photons. They travel at the speed of light, bounce off mirrors, are refracted by lenses, and are stopped by opaque barriers or filters of the wrong colour. Yet they do not trigger even the most sensitive detectors. The only thing in the universe that a shadow photon can be observed to affect is the tangible photon that it accompanies. This is the phenomenon of interference. Shadow photons would go entirely unnoticed were it not for this phenomenon and the strange patterns of shadows by which we observe it. Interference is not a special property of photons alone. Quantum theory predicts, and experiment confirms, that it occurs for every sort of particle. So there must be hosts of shadow neutrons accompanying every tangible neutron, hosts of shadow electrons accompanying every tangible electron, and so on. Each of these shadow particles is detectable only indirectly, through its interference with the motion of its tangible counterpart. It follows that reality is much bigger than it seems, and most of it is invisible. The objects and events that we in our instruments can directly observe are the merest tip of the iceberg. Now, tangible particles have a property that enables us to call them collectively a universe. This is simply their defining property of being tangible, that is, of interacting with each other and hence of being directly detectable by instruments and sense organs made by other tangible particles. Because of the phenomenon of interference, they are not wholly partitioned off from the rest of reality, that is, from the shadow particles. If they were, we should never have discovered there is more to reality than tangible particles. But to a good approximation, they do resemble the universe that we see around us in everyday life and the universe referred to in classical or pre-quantum physics. For similar reasons, we might think of calling the shadow particles collectively a parallel universe, for they too are affected by tangible particles only through interference phenomena. But we can do better than that, for it turns out that shadow particles are partitioned among themselves in exactly the same way as the universe of tangible particles is partitioned from them. In other words, they do not form a single homogeneous parallel universe, vastly larger than the tangible one, but rather a huge number of parallel universes, each similar in composition to the tangible one, and each obeying the same laws of physics, but differing in that the particles are in different positions in each universe. A remark about terminology. The word universe has traditionally been used to mean the whole of physical reality. In that sense, there can be at most one universe. We could stick to that definition and say that the entity we have been accustomed to calling the universe, namely all the directly perceptible matter and energy around us and the surrounding space, is not the whole universe after all, but only a small portion of it. Then we should have to invent a new name for that small tangible portion. But most physicists prefer to carry on using the word universe to denote the same entity that it has always denoted, even though that entity now turns out to be only a small part of physical reality. A new word, multiverse has been coined to denote physical reality as a whole. Single particle interference experiments, such as I have been describing, show us that the multiverse exists and it contains many counterparts of each particle in the tangible universe. To reach the further conclusion that the multiverse is roughly partitioned into parallel universes, we must consider interference phenomena involving more than one tangible particle. The simplest way of doing this is to ask by way of thought experiment what must be happening at the microscopic level when shadow photons strike an opaque object. They are stopped, of course. We know that because interference ceases when an opaque barrier is placed in the paths of shadow photons. But why? What stops them? We can rule out the straightforward answer that they are absorbed like tangible photons would be. Okay, and then David goes on to say, well, they're absorbed, these tangible photons are absorbed by tangible barriers, but it means that also the shadow photons are absorbed by shadow barriers. And the shadow barriers exist inside shadow laboratories, and the shadow laboratories are in a shadow world, and so on. And so this is the emergent multiverse idea. Okay, so there are our three experiments. There's some personal motivation and a hint about the multiverse. We still haven't got to reading any of chapter 11 of the multiverse, but that will happen next time. And we'll look in some detail at the further experiment. Okay, it's more of a thought experiment, but potentially could be really done. An experiment to refute other ways of understanding quantum theory, or trying to understand quantum theory, namely so-called collapse interpretations, or the Copenhagen interpretation, to refute those without refuting the multiverse theory. There is a test that David came up with, and so we'll talk about that next time. But for now, this has been nearly an hour's worth of quantum theory. Until next time, bye. If you're finding my videos, podcasts, or even my website valuable, there's a way to contribute now so that I can spend more time doing this. If you go to my website, www.bretthall.org, then you'll find a donate button there that links to a PayPal account. There's also Patreon, and you can find me there at Brett R. Hall. Thank you for any support at all. Know that it means a great deal to me. Thank you.